have graph is structured this is how a directed graph is structured. Now, these connections can tell us many things. For example, who influences who, and which people is from which group. Also, how some information is spreading in this community or in this network. So one way to understand this is to understand to identify the SCC or the strongly connected components in this graph. Now, this is how we can identify the SCCs in this simple example. Now, to do this, mostly we are familiar with the Tarzan's algorithm. And this Tarzan's algorithm has a very good time complexity, linear time complexity, where we can see the complexity is O(n) plus m. This n is the number of nodes, and m represents the number of edges.
Why? Time complexity is time. Why?
Yeah, because n is the number of nodes, and this node is visited exactly once when we use the Tarzan's algorithm. The same thing happens for edges. Each of the edge is also explored at most once a time. So it is O(n) and O(m) for edges. So in together it's O(n) plus m. This Tarzan's algorithm also memory efficient, and because it doesn't store the entire graph in some big structure or big memory. It just works on the fly when
why
the
it
graph.
can work on the fly?
Because for example, if the process starts from Ava and then it goes to Ven, and then it looks for the neighbors like Cleo or Ellie, and then it uses the DFS to find the next nodes, and it stores the data in a single stack and then get back to Ellie. So that's why it's O(n) time complexity for the memory. Now, although this works good, but it has some limitation. Like they work sequentially. Even if we have 64 cores in our machine, it can use only one core to explore and to identify the SCCs. Now, in this small example, although Tarzan's algorithm can work better, but what happens if we have millions of nodes? For example, if we think about Facebook, which has in practical 3 billions of users, and it also has the connections between these users like friendships, their likes, their follows, and many more things. So that can end up with hundreds of billions or even trillion of edges in this social graph. So in that case, we need to think about some parallel exploration of this graph, so we can parallelly process or parallelly identify the SCC algorithms from this graph. We can take the advantage of many cores. For example, if we have a 64 cores machine or more, we can use that. So this brings us to this new algorithm that we are going to see today, which is called Union Find Strongly Connected Components, or UFSCC. This is a multi-core and on-the-fly algorithm which preserves the features of Tarzan's algorithm, like using the on-the-fly property from the Tarzan's algorithm.
Why Tarzan's algorithm is so difficult? Why?
So if we look on this table, we can see the Tarzan's DFS. It's extremely difficult to parallelize because the DFS, we know it's P complete, right? And when we try to do that, managing the overlapping stack of the stacks of the Tarzan's algorithm, we know the Tarzan's algorithm use the stacks, and also the cycles between the threads, that becomes very hard to do. And you can learn more about this one on the citation that I have kept in the slide corner. Now, if we think about like this Tarzan's algorithm, they have the on-the-fly reporting. So that means we don't need to explore the whole graph or need to store the whole graph in memory before we look for the SCC. For example, if we think about the verification graph or the model checking graph or the online graphs, we don't have the whole graph on hand or like that this kind of dynamic graphs for Facebook. So we need to find the SCCs on the fly in that case. Another mostly recognized approach is the BFS based algorithms. We know the BFS work as layer, right? So that is possible to parallelize. But the hard thing is we need the graph on hand to do that. So we need the we cannot use the on the fly reporting feature on BFS based algorithm.
Why a database cannot use on the fly?
Because when we are exploring the nodes, we need to store the data in queue, and we need to explore. We need to know the whole graph in that case.
Not very correct. Oh.
Uh,
Go on, you can go on.
okay. Here
After the BW, it uses set intersections. From FW, you get a set. And the BW search, the FW, the forward search, get a set. And the backward, you get a set. And you must merge and get the intersection of two sets. That's get SCC.
Yeah.
And you must store the two sets in the memory. That's
okay.
It must be loaded the whole graph into the memory.
Okay. Now, for UFSCC, we are looking the feature in UFSCC that can combine the both of these. Like it can offer the parallelized version to find the SCCs, as well as it can preserve the on-the-fly reporting feature from the Tarzan's algorithm.
Go on.
Okay. Okay. Now, to understand this UFSCC, we need to understand at first what is the PRDFS. That is something from that is the first thing we need to understand here. So, in this one, when we are talking about the parallel randomized DFS or PRDFS, instead of running one DFS like the Tarzan's algorithm, UFSCC runs many DFS in parallel. Like one per worker. For example, if we are calling peer DFS, each worker picks a random unvisited node. They will pick any nodes randomly. So in our this example, maybe two workers are picking two nodes A and G. Now, if we think how it works, so they at first explore A and G, and then they explore the next one like B and E, and next C and F, and then the orange worker, they have found SCC or a package to G, and the green one will find another package to A. So in that case, they use two local stack for themselves, and then they identify the two SCCs, and they build their own DFS trace. This is how simply if we say like how the peer DFS works. Now,
Hey, question. Your B is randomly walk to C. Why your B cannot randomly walk to E?
so because it's not something like it cannot go to E. It what we said, like it picks the next nodes randomly, and it also so that's why we are assuming now it's going to C, not E.
But you say it's randomly. It's possible go to E, not C.
Yeah, it's possible.
Oh, yes.
It's possible it can go to E. But for simplicity, we are picking like here, it can go to C. So this is how the PRDFS works here. But the idea is of our algorithm is the EFSCC is what will happen if we have a very big SCC. For example, if we had a connection from G to C, So in that case, maybe two workers could work for this side one worker, and for this side another worker. And in UFSCC, we can simply merge them without exploring the whole graphs with a lot of time. So this is the main idea of UFSCC that we will see in next case. But the question is, how can we do that? How can we merge to explode tree, or these two trees? So here it comes the union find data structure. Just one moment, I need to clean my screen.
Yeah, freezing.
My screen is need to clean. Yeah. Good. Okay. Now, that is what I was saying. Like, what if the DFS trees overlap or touch? So, if they are in one SCC, maybe we can merge them, or we need to manage these things. So that's why we use the union find data structure. But before we go for the union find algorithm, let's talk about the time complexities for the BFS based or the fixed point BFS based parallel algorithm versus the paired DFS. Why we are picking the paired DFS here? Why we want to use paired DFS for our EFSCC? Now, if we think about the fixed point based BFS parallel version parallel algorithms, we can see the time complexity here for the best case scenario. The fixed point BFS and paired DFS, they are almost same. They are acting same. In work, so linear time is split over into P processor. If we have P processor, the linear time like n plus m, it will be split over the P processor or P workers. And what is the workload? Complexity. It will be the same. It will be the O n plus m, because it will explore the nodes and the edges once. So it's the same. But we can see in paired DFS we need the less memory, because we don't need to store the.
The pointer. They can point it out. I will know where is that. Where are you talking?
Yeah.
Here.
Sorry. So it need the less memory, because we don't need to store the full edge set into our memory for the paired DFS. Now if we think about the worst case, so worst case means when we can have the worst case. So worst case, if we have many small SCC, so that will ends up with high contention in our work, right? So traditional methods, like if we think about the fixed point BFS, they might show a slowdown, and it will come to m dot log n, because maybe because they will have to revisit the edges. So that's why the time complexity and the work complexity here, it will come down to m dot log n. And in case of memory is the same. But if we see the paired DFS, paired DFS keeps the time linear. So because they're randomly and in parallel, they are exploring the nodes. So that's why we can get n plus m complexity even if in worst case.
Good.
And
Good. Go on.
Okay, thank you. And in case of worst case, our parallel worker can like P processors need to work more, does more total work. So that's why it's P dot n plus m. And if we think about the memory scales, it will be P dot n, because each worker may have to hold its own stack for up to n nodes, right? So because we see like in parallel version, we have each of the worker has their own stack, right? So if we have a very small SCCs, like all of them are small SCCs, think about we have 10 nodes and 10 of these nodes are SCCs. So in that case, we will each of these worker will pick their own stack. So that will ends up with P dot n.
Good. Go on.
Okay, thank you. Let me clean this screen first. Next. Okay, now let's see before we go to the actual UFSCC of the parallel version of the SCC exploration using the union find data structure. Let's see how it works for a sequential set based case, like when we have only one worker. Let's see how it explores. So the union find structure propose we use the set. So in that case. Each node belongs to a disjoint set. They will prepare that disjoint set. So, for example, as V equals to V set. So, if we think about A, it should be as A equals to A. For B, it should be as B equals to B, and so on. For all, we can see at the right side. So, for all of these nodes, they have their they have their all disjoint set. Now, let's perform a DFS here. Now, if we start, if we think about our time like T1, at time T1, the worker may have started working from A. Now it will go to the next node like B, and we know it can go to E or C either, but we are picking for simplicity, it can go to C, and then it can maybe go to D. Now it will find a package to A. Now, when it find a package, next time, it will see like A is visited, right? And it is also not dead. So that means it is in its own stack. So when it is C, it is still in its own stack. It will use the union find algorithm to merge all of them into a tree. Click not working. Okay. Now we can now pop the stack, and we can make our tree here. So here C is the representative node, and D is its child. And when we pop B, we are keeping it at the top. We can see this expression. So it will make B as the top, and then A as the top of this tree.
Great. How much time spent on union? Time complexity.
It is something used by the Ackermann function. It is very less and almost constant. Now, the same thing will happen for the right side of our. Okay. So before do that, it will now assign all of these four sets as date, which will also unionize to the date set. And now our stack is free. Now we can keep explore the next nodes. Like we can start exploring from E. Sorry. One more thing I would like to say. So at this point, if for some reason we need to find any of these nodes in this set, if we do that, so then this tree will be flattened because of the find set algorithm, and it all of these nodes will directly points to the representative node like the A. Now, let's go back. Let's see. So if we keep continuing exploring to the right side, so we can see our next node is E, and it will keep exploring F, and it will keep exploring G, and so on. And it will again find another package, and it will pop all of them, and the same to the left side, and it will make another tree like EFG.
Oh, question. How can I test that A and B are in the same SCC? The form here. From here.
Sorry?
How can I test that? You already finished the SCC decomposition. How can I test A and B are in the same SCC?
Because they are in a same supernode right now. So if we just run the find set for B or A, we will find them in this supernode.
Okay, go on.
Sorry. Okay. Now, this is the time complexity that I already talked about in last slide when I was answering the question. So the time complexity here is the Ackermann function is just alpha n. We can learn more about this from the textbook that I have referenced in the corner of the slide. Now let's take a look on the core topic of the union find SCC algorithm. Now let's see how this works. So the basic core idea is instead of running a sequential version of the SCC that we have seen before in our slide, we can use multiple workers, maybe 2, 3, or more many workers that we have in large graphs. So in this example, we will see with 2 workers, worker 1, W1, and worker 2 as W2. Now let's walk through this presentation. So think about at time 1, T1, W1 claims and visits the node A randomly, and W2 claims and visits the node E. So randomly they have picked 2 nodes. It could be possible they pick any other node, but just for simplicity, we are thinking of this like now, on their next time, T2, they will visit their next immediate nodes, of course, B and F. Now, at point B, it can go to E or it can go to C. But B will see like it can randomly go to E or C, but B will go for C for this example, and the W2 is going to G. And in time 4, W2 can find its backends. So when it will find a backends here, it will try to develop its own tree. Now it will pop the stack like our before example that we have seen. It will okay, I think I have picked a wrong animation here. It should be EFG, the next one. And when W1 will find its backends from D to A, it will pick its tree A, B, C, D. We can see here. Now the question is how we handle if we had a connection from G to C. Let's assume we have a connection from D to C. So that means it's not a 2 SCC, but it's a big 1 SCC, right? So in that case, if we have just pure DFS or the Tarzans, they will sequentially browse all of these nodes and then find the big SCC, big 1 SCC. But the idea of the EFSCC is here, like we can merge these explode two SCCs into one. So that's why if we have a big graphs like millions of nodes in one SCC, we can use we can explore them with our workers, and then we can merge them. We can merge them using the union find set. So that's why we are looking to union C and G here. Suppose at this point, if any worker look for G or C, any one of these nodes, they will find, for example, if a worker come here and it will find E, so it will see it's in a supernode of this tree. So then if it explores, there is a connection between this one with C, so it can union them. Now, we can in that case we can end up with this kind of tree with one SCC. We can merge the two trees and can get this one.
It's only take constant time. It's efficient.
Yeah.
Oh, yeah.
Just clean it. Yeah. Okay. Now, we have done some experimental reviews on this UFSCC. So these experiments were ran on 64 core machine, and it was compared with sequential Tarzan's algorithm, where keeping the Tarzan's algorithm as the baseline, and also Tarzan's algorithm were compared with parallel Reynolds with the peer DFS. If you'd like to learn more about this DFS or the parallel Reynolds version, you can take the advantage of this reference paper. Now, in this presentation, and the original experiment were ran for many kind of graphs, but in this presentation, we will look for a specific type of graphs, which is we say verification graph or the model graphs. So here are the characteristics of this model checking graphs. If you'd like to know more about the model checking graphs, there is a reference is given. So in this example, we can see each row shows the number of vertices for each of this graph or the edges. It also shows the transition or the vertices or the nodes and the number of transitions or the edges. It also shows the number of SCCs in that graph and maximum SCC size. For example, we can see in the leader filter graph, its maximum SCC size was 1. So that means when it has nodes 26.3, in all of these 26.3 millions are SCCs. It also describes the diameter. So what the diameter means? The diameter of a graph is meaning like its longest shortest path between any two nodes. So for example, if we think about Tarzan's algorithm, it has to do the DFS for 71 nodes here. So that is the diameter. So here we have around 6 graphs. Each of these has some different behavior, and now we will see how they works when actually they were tested. Okay, now let's talk about the first graph, the leader filter one. So, sorry. Okay. So let's first understand how this graphs is taken is drawn. So we can see the x-axis it denotes the number of workers. So we have 1, 2, and up to 64 workers. And the y-axis it represents the speed up versus Tarzan. So we will always see the Tarzan's algorithm like this green. It's flat into one. And this Tarzan's algorithm is the base, and it will be compared with Reynolds and UFSCC. So we can see the blue one is representing the UFSCC, and the red one, it will represent the Reynolds. Now, if we again look on this leaders filter, we see it has 26.3 million vertices, and the maximum SCC size is 1. So that is the main feature, main thing that we need to look on this experiment. So when our SCC size is just 1, we see the Reynolds is working better than the UFSCC. Now the question is why? Because we have seen the UFSCC is taking the main advantage over the peer DFS is that it can explore the nodes with parallel workers, and then it can merge them using the union find. So that was the main core idea of the UFSCC. So in that case, Reynolds is already working better than the UFSCC algorithm.
Yes. You have a 60 for cost. Why is the best case is only 32 speed ups? Is that so? In the it has the best performance with 32 cores. Oh, sorry, it's 60 for cores. So why it's only
It's not the 32 cores. It's just saying 32 times or around 35 times faster than the Tarzan's algorithm.
Yes, why is that huge gap here? Because we have 60 for cores and we expect here 60 for speed ups.
It's not something like we have 64 cores and the nodes are only 64. So then we could say like 64 nodes can pick 64 nodes. It has millions of nodes. So we are just comparing how Tarzan's algorithm works on all of these nodes and how how Renault and UFSCC worked using these multiple workers on the same case. So this is just the speed up, like how speedy.
Why is we use 64 cores but only get the 32 speed ups? If you don't know, you can say I don't know.
Yeah, I was just thinking one moment. I think uh, I think that's all I know here. Okay. No, I don't know.
Make it clear later. Okay. Write into a
Okay.
report.
Okay. Thank you. Let's go for the next one. Okay. So the next one is the bakery graph. So this one has the feature is that it has a maximum SCC size is 8.6 million. So that means we can see when we have 11.8 million of nodes or vertices, and it has 8.6 million size of the SCC size. So that means it has a huge SCC. So in that case, we see our UFSCC versus Tarzan is 27 times faster when we ran the experiment, and this and UFSCC versus with the Tarzans, and with the if we think about Renault, it is also much faster than the Renault. Now, yeah. One more thing is why Renault is falling.
Yeah, here it's doesn't have a 64 cores. It doesn't have any speed up, and even it's much slower than sequential version. And why we use this renowned actually? It's slower than sequential version. Why?
Because the same thing, like because we see Renault is DFS, like it runs the parallel DFS. So when it is picking the nodes in parallel when we have a big SCC. So that means although the workers is picking some nodes from that SCC, it's not coming end up with a merge. So that's why it's falling.
Okay. Okay, really bad. That's really bad. In this case, Ronaldo is really bad.
Yeah. Because yeah, although if it is trying to randomly pick the nodes, but it's ending up uh without margin. So that is because they don't have the margin option, so they still working like the Tarzans.
Yeah. So that's why I say Ronaldo is a parallel and slower than the sequential version. It's meaningless.
Yeah.
Useless, meaningless. Okay. Go on.
The next one is the third one is Cambridge. So this is the Cambridge. This is the third algorithm we see here. Cambridge. So uh, it does not have a lot of SCCs. We can see only 8,413 SCCs, while we have 3.4 million nodes. And one of these SCC is 3.3 million. So we can say it is a mix, something like our previous two graphs or previous two graphs. So we can see after the experiments, like UFSCC speed up around 20 times faster than the Tarzan's algorithm, and from the Renault it was also much better. So the same answer here, because Renault is falling because we have a very big SCC here. So where Renault is struggling, it's performing flat. Simply we can say it's because of the memory contention. And the exploration order is also matter in when we have high core counts.
Go on.
Let's go for the next one. And this is the another graph, the lab graph. So we can see in this one we have only one SCC. So and the entire graph is one SCC. So in that case, the EFSCC versus Tarzan is 11 times faster, where EFSCC versus Renault was still worked better. Yeah. think that's all for this graph is noticeable. Let's go for the next one. Now we see another graph, the resistance graph. In this one, we can see the maximum SCC size is 13.8 million, where we have the vertices. So we have only 3 SCCs, and one of the SCCs is very big. It's 13.8 million, almost the same as the number of nodes. So and one more thing is noticeable, its diameter is very high. So in that case, Tarzan takes maybe a very long time to explore this graph, because Tarzan will do DFS into this huge diameter graph, right? So UFSCC spreads the work because UFSCC can merge the partially building trees, and so that's why UFSCC will work better here. And again, Reynolds is falling because
I tell you the best performance with 16 cores. 16 cores. We have 64 cores. 16 cores already go to the best performance. Also have wasted. It's millions.
Because that may be like after 16, maybe it is having some having the trouble with the memory contention. One thing I have noticed in the Tarzan's algorithm. Can I go back to my slide? Okay. So in this picture, one thing I was thinking is when we have 2 workers, suppose W1 and W2, and if we think about like they are exploring this. So if this kind of thing happen, like suppose this is W1, sorry, and this is W2. So if worker 1 start from B at time 1, worker 2 start from A. So worker 1 will go to the next one, worker 2 come to here, and then worker 1 again go for the next one, it will come to here. So they will just follow up each other, and they will take the same time just to find the one SCC, almost the same time. If it is a very big graph, 2 worker will go work for the same thing.
That's a good explanation. Yes, it is. It's 2 workers on the same SCC. You see, it don't have any speed up.
Yeah, and this thing can happen when you have even 64 cores. So maybe that was a very big diameter graph, right? So for example, it is only 4 nodes. What happen if we have 7 nodes? So what happened when we have 7 million nodes? So then many workers will just keep following each other. It will just waste their time.
Yes, and it's randomly, you cannot control. So sometimes it's good, sometimes bad.
Yes.
That is the worst case. Can you go back to the worst case of a time compliant analysis? Worst case. That is the worst case.
Yeah, so that is the worst case in PRDFS. We didn't talk about this.
In the time compliant analysis.
Yeah, I'm looking for that.
Yes, worst case. You see the worst case. Time is
This is the work.
It's a work. The time is still linear.
Yeah.
Don't have any speed ups. This is worst case. Worst case, don't have any speed ups. But the best case.
Yeah, but this one is for PRDFS, but that we'll see on UFSCC.
Oh, not the UF. Okay.
Okay.
Oh, not yet discussed that. Yeah, go
on. I'm looking for my cursor. Okay. We should go for here. It's first. Okay. Now this is our last graph for our presentation here. So the sorter graph. In this graph, we can see the one of the SCC is 1.2 million, which is the same as the same as the number of nodes, and it has a maximum SCC size 278. So we can see it has many tiny SCCs. It's not like only one node SCC. It's tiny SCC. Maybe 2 or 3 nodes is building their SCCs. So in that case, EFSCC will see overhead because the EFSCC compared to Reynolds was it could merge the SCCs, partially explode SCCs, right? But in this case, because we have a small tiny SCCs, Reynolds can work better in that case than the EFSCC actually. So overall, after end of these experiments, we have seen the UFSCC achieves almost 10 to 35 times the speed of our targets. If we combine all of these experiments, it also shows better scalability than Reynolds when we increase the number of cores or number of workers. During the experiment, it was also shown that it also efficiently used the memory, like storing the information in the memory, like the stack about the next pointer, etc. For each one of these edges. And it also showed a low exploration overhead. It was only around 2% for per workers.
Low rate exploration. Go on. Yeah.
So one future work could be to use the MCAS over the CAS. So in current experiments, they have used atomic compare and swap operation with some fine-grained locks. If we read the paper, we will see it on algorithm 5. So they did the root pointer updates, cyclic list merging, and worker set coordination with CAS and sometime fine-grained locks. So one proposed solution maybe we could use to update the super nodes when merging, use the MCAS or the multi-word compare and swap. So my expectation benefits is maybe we can get some fully lock-free partial SCC merge. And it maybe can improve the scalability under high contention when we have a lot of threads or workers.
Good.
So that's all my references in detail that I keep in the corner of my slides.
Good. I have several questions, 2 questions left. So can you go back to your experiment data graphs? So why all your experiment data graphs are verification network? Did you test on the social networks?
Yeah, we also tested on the social network graphs, but for the presentation purposes, we kept it short. There is a reference is added at the corner of this slide. If you'd like to see the other types of experiments, you can go on this paper.
Okay. And the second question, is it possible to have deadlocks? You see the multiple workers doing the SCC decomposition. Is that possible to have deadlock?
So just give me 1 second so I can think. If we go on this picture, we can understand things better. So if we think about in this picture here, so maybe one of the worker can start from A and then browse B, and another worker W2, they can start from C and go for D. And now it will look forward for the next one, and it can look forward for the previous one. So it will not see like it is visited by other nodes because they are storing this information into their local stack. So I don't think there should be a deadlock. They will keep browsing.
Like a repeated traversing.
Yeah, it will repeat the traversing, but
still from C to D to A, repeated traverse this.
Yeah, it will do the same work that other worker already have done, because the algorithm that is written for the UFSCC, they don't look for the other workers update, like what they are currently browsing.
Okay, I still have question. You see, yes, 2 workers are working like this, just repeatedly traversing. How can you merge these 2 SCCs? Merge these 2 SCCs. two workers. So you need some synchronization.
So that's why we are using the union find algorithm sets.
And unified access, but how about the two workers accessing the same unified data structure? Do you need a lock? Lock where? Where we should lock?
So in that case, we need to log the representative nodes.
Do you mean A? This one?
Yeah.
Lock it. So we'll still need lock.
Yeah. So we need to log the representative node in that
Is it
case.
possible that to make it lock free?
Sorry?
Lock free. Just because this paper is use lock to merge.
Yeah. So that's why we are talking like maybe we can introduce the lock-free version using the multi-word compare swap.
Good.
To update the root. That's what I was saying here. Like we can use this one to update the supernode root pointers.
So what's the benefit of lock free?
Uh,
Lock is simple. Lock free is very complicated. We must
so that
benefits.
So the lock free can give one advantage, like in our previous picture when we see, for example, you said here. So when we have although we have already this speed up, but for the 64 works, it was something like this. So maybe if we can when we have locks, it's bringing some high contention because of the locks. But if it is lock free, maybe more workers can contribute better.
Great, explained very clear. That's all my question.
Thank you.
Do you have any questions? No? Try. It's a good opportunity. Ask any questions. Ask any questions. Like how much time spent on this slides? This prepare the slides. Igor, do you have any questions?
No, I'm good.
We have time. Yeah.
I'm good. Yep.
Good. No? Try ask one question. Okay. So ask one question. Yeah. Ask. Yeah. If you don't ask, I will ask you. Yes. I'll go back to the unified data structure. Unified data structure.
One moment, sorry, I'm going.
So yeah. No. Oh yeah. Unified.
Union find data structure. So it's here.
Yes. That's my idea is you see the unified data structure here. The two cells is unit together only takes a constant time. So this can be used to merge the tree nodes. Tree nodes with the two tree nodes. In that paper, the tree nodes, the merge two tree nodes will traverse the whole all the vertices in the tree nodes. So this will only take constant time. But this is the basic. This is only the basic data structure. We need link them together, link them together, and also maybe maintain the equal trust that way. So if we use this data structure, we can simplify and improve the time complexity. So that's why do some research on this. Read the Zarif's report about this unified data structure and the unified data structure. That's all my question. You did great work.
Yeah. Thank you so much.
So we don't know any other questions. Last chance. If you don't have, that is today's talk. Okay, I will stop the recording.